stuff. So today, let me teach you about the temperature coefficient.
Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.
Are you looking at an online advanced secondary school that can teach you to master, enjoy, and love advanced physics, advanced chemistry, advanced mathematics, and best applied mathematics? That might be one of your questions that you've been wondering around. But I want to tell you that today, fortunately, you met with the right answer. We are here in order to teach and train advanced secondary students to extract knowledge, understanding, and wisdom from the classroom instruction and combine it with knowledge, understanding, and wisdom that will teach them to extract it from the Word of God in order to solve real-life problems. How are you, everybody who is watching this program? My name is Olenjolai. I'm from Tanzania. I would like to take this opportunity to welcome all the local, national, and international students into this fantastic session of current electricity. So right now, let me just take you directly and introduce you some of the information that I've written on the blackboard before we dive into the session 8. Welcome into Tanzania Online Advanced Secondary School in square bracket Olenjolai M, and simultaneously welcome into one of our official YouTube channel that called Tanzania Online Level 6 School in square bracket Olenjolai M. So welcome into Departments of Advanced Physics and welcome into the subject of the day that called Advanced Physics. And this is the main topic 2 that called current electricity. And we dedicate these contents to Form 6 students, Form 6 students, reciter students, Grade 12 students, QT students, teachers who are teaching advanced physics and physicists and hobbyists of physics. And we are in chapter 1 that called the electrical conductions of metals. And this is session 8 where we are teaching you the concept called temperature coefficient of resistance. Temperature coefficient of resistance. Temperature coefficient of resistance. Okay, so are you ready for that? Okay, so this is session 8. You can access the previous session in our official YouTube channel that called Tanzania Online Level 6 School in square bracket Olenjolai M. And right now, let me just take you into the quick review of previous session. If you have any question, you can interact with me where you are at any time, so the comment section below. So in session 7, simply I've talked about Ohm's law. So the resistance of the conductor might be changing. Okay, so let us go into the subject of the day. Temperature coefficient. So we have a fundamental question for Olenjolai. This is question number 1. What is temperature coefficient? What is temperature coefficient? What is temperature coefficient of resistance? What is temperature coefficient of resistance? That's a fundamental question that we have. What the temperature coefficient of 40 of resistance? So I have formed 2 definitions. So temperature coefficient of resistance is a fractional increase in resistance per unity temperature rise of a conductor. Per unity temperature rise of conductor. So temperature coefficient of resistance is a fractional increase. A fractional increase per unity temperature rise of a conductor. Or temperature coefficient is the increase in resistance per original resistance per rising temperature. Per original resistance per rising temperature. So we say that temperature coefficient of resistance is a fractional increase in resistance per unity temperature rise. So we should have a temperature rise in the conductor, which will cause the fractional increase in resistance. So it means that the fractional increase, so we say that if you have change in temperature, for example, if you have change in temperature, this change in temperature will influence the change of resistance of conductor. That's what we are. That's what we are building in our mindset. So I say that resistance of metallic conductor, resistance of metallic conductor, resistance of metallic conductors, resistance of metallic conductor increase linear due to rise in temperature. Due to rise in temperature. So resistance of metallic conductors increase linearly due to rise in what? In temperature. So mathematically, the temperature coefficient of resistance temperature coefficient of resistance. This is equal to the fractional change in resistance of the conductor due to fractional change in length, or due to original resistance or resistance of the conductor, and also change in temperature. So the temperature coefficient of resistance is alpha, at the symbol. So you say that whereby alpha, this is coefficient, this is temperature coefficient of resistance, and R naught, this is original resistance. Then we have change in theta. This is change in temperature. Change in temperature. So temperature coefficient of resistance temperature coefficient of resistance is equal to the change in resistance of original resistance times change in temperature. So temperature coefficient of resistance alpha is given by that formula. So you say again that in physics, change in resistance can be represented as delta R, and change in temperature can be represented as delta theta. So the temperature coefficient of resistance is equal to delta R of resistance, original resistance of the conductor, times delta theta. So now, let me take you into the derivation of the formula. Derivation of the formula that relates original resistance at any temperature, then temperature theta, and temperature coefficient of resistance. So first stage. So recall temperature coefficient of resistance is equal to change in resistance over original resistance of the conductor times change in temperature. So temperature coefficient of resistance is equal to the R over original resistance of resistance, then the theta. So this over 1, so cross multiplication. We have temperature coefficient of resistance R naught and theta is equal to delta R. So we have delta R is equal to alpha resistance of the conductor theta delta R is equal to alpha times resistance of the OT of the conductor times small change in OT and theta. So the second step, suppose that this is equation 1. So apply integration to both sides of 40 of equation 2. This is equation 2, that equation 1, this is equation 1. Or this one is equation 1, whatever the case, it's still equation 1. So listen, so we have left-hand side and right-hand side. So on left-hand side, we are integrating from original resistance of the conductor before temperature rise to the particular resistance at temperature theta of the R. This is equal to the integral from what? From theta 1, let's say, or initial temperature, to the final temperature of what? Of temperature of coefficient, resistance of 40 of the conductor, the theta. Okay? So usual, here we have R power 0. So you have R power 0. This is resistance naught. To this resistance is equal to what? Is equal to alpha R naught. And then we integrate from initial temperature to final temperature of what? Of the theta. So 0 power 1 over what is, so it means it is R. So on the left hand side we have resistance, so we substitute the upper limit, which is resistance R. Listen careful, stop writing. We have something that we invade, or it means that we use from mathematics point of view. So introduce resistance here, then minus the lower limit, which is original resistance before the temperature rise. So this is temperature coefficient times original resistance of the conductor, and then so this side we have what? Initial temperature, we have theta power 0, d theta, here we have final temperature. So we have resistance at any temperature theta, so this is equal to R minus R naught, I'll introduce there, then alpha times R naught. When we integrate theta power 0, we get theta power 1 from theta initial to final temperature. So we say that resistance at any temperature, R naught, this is equal to R times what? Times, wait, I have made a mistake. I've made a mistake from this second part. So please do that minor correction, excuse me. I've made a mistake in this derivation. This is the mistake that I did. You have to separate the variables. Okay, you have to separate the variables. So on this side, divide by R naught. On this side, divide by R naught. R naught is resistance before the resistance of the conductor before temperature, before the rising temperature. So this one cancel. Alpha d theta is equal to what? The R over R naught. So the R over R naught is equal to alpha B theta. So this will be our equation 2. So we should integrate it from this concept. Call it R naught or R. Okay. Okay. So he said that we know that we say from this point, let R naught to be R, to be instantaneous resistance. So we say that small change in resistance over the resistance at any temperature is equal to temperature coefficient times change in temperature. Temperature coefficient of resistance of the conductor times change in temperature. So simply, our equation 2 is dR over R. This is equal to temperature coefficient of resistance times small change in theta. So this is equation 2. So the second step of this derivation, introduce integration to both sides. So we have the R over R. This is equal to alpha d theta. So here we integrate from original resistance before the change in resistance due to the rise of temperature. On this side, we also integrate from initial temperature to the final temperature. Okay? So if this is the case, we go into the steady state. You can consider that this now is a set equation which includes integrands or integration sign on left and right hand side. So we go into the steady state. Let us consider left hand side of equation 1. So the left hand side of equation 1 is integral from R naught to R of dR of R. So if you're integrating the something over something, you get ln of something.
Yes.
When integrating the R over R, you get ln of R. When integrating the theta over theta, you get ln of theta. When integrating the L over L, you get ln of L. When integrating the A over A, you get ln of A. Bear that in mind. These are the principles of logarithm, of integrating logarithmic function. So it means that if integrating the R over R, the response, the R over R, the response is ln of R. Then our lower limit is from initial resistance to final resistance. That will change afterwards, after a particular time.
Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto.
Delta R is equal to alpha times resistance of the of the conductor times small change in voltage. So the second resistance due to the rise of temperature. On this side, we also integrate from initial temperature to the final temperature. Okay? So if this is the case, we go into the third stage. You can consider this now is the third equation, which includes integrands or integration sign on left and right hand side. So we go into the third stage. Let us consider left hand side of equation 1. So the left hand side of equation 1 is integral from R0 to R of dr of R. So if you're integrating the something over something, you get ln of something.
Yes.
When integrating the R over R, you get ln of R. When integrating the theta over theta, you get ln of theta. When integrating the L over L, you get ln of L. When integrating the A over A, you get ln of A. Bear that in mind. These are the principles of logarithm, of integrating logarithmic function. So it means that if integrating the R over R, the response, the R over R, the response is ln of R. Then our lower limit is from initial resistance to final resistance. That will change after watching after a particular time. So on left hand side we have ln of R from R0 to R. This is equal to ln of R minus ln of R0. Also from laws of logarithm, ln of R minus ln of R0 from laws of logarithm. If you substitute two logarithmic functions, is equal to the division of those two logarithmic functions. So ln of R minus ln of R0 is equal to ln of R over R0. Simply left hand side, we are integrating from R0 to R, dr over R. This is equal to ln of resistance of the conductor over original resistance of the conductor. So this is our equation 4. That's the integral of left hand side. Now we are going to integrate the first stage, then integrate left hand side of equation 3. Integrate left hand side of equation 3. So you're integrating from theta initial, theta final, alpha d theta. So this is equal to alpha integral from initial temperature to final temperature of the theta. This is equal to alpha of theta from initial temperature to final temperature. So if you're integrating from initial temperature to final temperature, which something can call d theta 1 to theta 2, alpha d theta, this will make it temperature coefficient of resistance, and then here we have final temperature minus initial temperature. So this will make equation 5. So the fifth step, now let us equate equation 4 with equation 5. So the result of what you've got on the Question 4, it is ln of R over R naught. This is equal to alpha. Then we say what? The final initial temperature. So this will make equation 6. So this is still not a fine expression of the final formula determining resistance of the conductor at any temperature. We have to do some work ahead. So this is the fifth step. Express equation 6 in exponential form. So to express an exponential form, you have to listen. Having ln of resistance at any temperature of our resistance of the conductor at initial temperature, this is equal to, if you write it as log of E or log of R over R naught plus E. So simply we say that log of E or log of R over R naught plus E is equal to temperature coefficient minus temperature coefficient times what? Final temperature minus initial temperature like this. So this is still logarithmic form. Listen, this is still logarithmic form. This is log, this is base, this is a number. So to express in exponential form, this become a base, this become exponent, this become a number. Right?
Yes.
The simple meaning, we have taught you how you can express maybe log of A plus 10 is equal to C. So if you express in exponential form, it will be 10 power C is equal to A. So the same principle here. So the base is E. So E power temperature coefficient of resistance times final temperature minus initial temperature. This is equal to resistance at any temperature over resistance at initial temperature, which is R naught, like that. So make this resistance the subject. So to make it the subject, we multiply by R naught to both sides, multiply by R naught. So for that case, on the left hand side you have R naught, E power temperature coefficient, final temperature minus initial temperature. This is equal to what? Is equal to R. So resistance of a conductor at any temperature. So resistance of the conductor at any temperature R. This is given as product of resistance of the conductor at initial temperature multiplied by a number which is E power alpha, which is temperature coefficient of the conductor, final temperature minus initial temperature. So this is the formula that we need to do computation in this case. So in this formula, whereby R, this is resistance of conductor at any temperature, this is the resistance conductor at initial temperature alpha, this is temperature coefficient, temperature coefficient of resistance, conductor, then final, this is final temperature, final temperature of conductor, and this is initial temperature. So even this one can call the RI, depend, but most of the books you can find are not. This one also you can call it theta 2, and this is theta 1, and R, this one also R, in some of the books you can find is R at theta. So it means resistance of the conductor at any temperature. So it's beautiful to deal with this derivation. And first of all, we call that once. Okay, so these are just some few terms. So you can have R or R theta patterns. But we are still in the middle of our derivation. So R is equal to R out, R naught, E or alpha, let's say theta 2 minus theta 1. Or theta final, maybe final temperature minus initial temperature. So this is still an exponential. We don't want this formula to be exponential. Let us express it in algebraic. So Roman 6, you say that express equation 7. Equation 7 in algebraic form. Algebraic form. Okay, so we have this expression R is equal to R naught, E or alpha, theta final minus initial temperature. So divide by resistance of the conductor at temperature 0, resistance of conductor at temperature 0. So this one will cancel. So this is R naught, hence is equal to E or alpha final temperature minus initial temperature. So this is still equation 7, but we just expressed in another form. So to express it in algebraic form, because it is in exponential form, to express this equation in 7 in algebraic form, we go into the 6th step. 6th step, we say that we call the binomial expansion. So the binomial expansion of what? Of E. E is a number, so we say that in binomial expansions in mathematics, we say that E or X is equal to 1 plus what? So 1 plus Xe. So I say 1 plus Xe. So 1 plus Xe plus X squared over 2 factorial plus X cubic over 3 factorial plus H. We don't need to deal with high power. So stop writing, especially for those students who are not pursuing advanced mathematics. For the PCB students, stop writing and listen carefully what we are doing here as mathematicians. The binomial expansions of e power x is e power x. It means if you expand e power x, say stop writing. In mathematics, we get 1 plus x squared over 2 factorial plus x cubic over 3 factorial plus x power 4 over 4 factorial plus h. So in physics, listen, I say PCB, all of you are PCB here. You're still copying. In physics, means that in physics, we ignore higher powers, powers of 40 of any binomial expansion. If you've been learning gravitation, you have learned something like this. So in mathematics, so in physics, we just ignore all of these terms. We just need these two. First term and second term to simplify life. Right? So you say now the binomial expansion of e power x is equal to 1 plus x. Where does this x come from? This one. I say stop writing. And even the PCM student, the PMC, the Pgm student, stop writing because we are not recalling the whole part of binomial expansions of e. We're just recalling first and second term. So we want to simplify life. So e power x is equal to 1 plus x. What do we have in equation on right hand side of equation 7? We have e power alpha times this one. Right? Simply we have e power alpha times final temperature minus initial temperature, which in other words you can say that you have e power alpha times change in temperature. Do you agree?
Yes.
Okay. So if this is the case, if we compare it, so now we have e power alpha small change in temperature. If we use this expansion, what will we have? The first term will be 1 plus x. What is our x in here? Alpha times small change in temperature. Okay?
Yes.
That's what we wanted. So this will make your equation 8. So equation 8 is equal to equation 7. So this is the 7th state. 7th state, equation 7 is equal to equation 8. What is equation 8? Resistance at any temperature over resistance at initial temperature is equal to what? Initially it was E power alpha, final temperature minus initial temperature, and this we say is equal to E power alpha change in theta, and this by binomial expansion is equal to 1 plus temperature coefficient times small change in temperature. Are we together?
Yes.
So now we have converted our formula from logarithmic into exponential form and conveyed from exponential form into algebraic form. So you agree with me that resistance at any temperature over resistance at temperature at initial temperature is equal to 1 plus alpha theta. Changing what? Changing theta. Do you agree with me?
Yeah.
Huh?
Yes.
Okay. So if that's the case, we can apply by temperature or initial temperature to both sides of this equation. So this one and this one are cancelled. resistance at any temperature. So you see now, the equation is in algebraic. So this is what we call the algebraic form, where R stands for resistance of the conductor at any temperature. This R stands for resistance of the conductor before temperature rise. 1 is the constant numbers 1. Alpha stands for temperature coefficient of resistance of conductor. Delta theta stands for change in temperature. Okay, this is the final expression that we'll be using. Is it interesting? Yeah, so it's interesting if you have understood it, but it's challenging if you didn't understand. But if you didn't understand, just review the derivation from the beginnings to that point. It's not difficult the way that you think. So, or you can write this expression that R at temperature theta, as I have explained, is equal to R naught in sum of the books or sum of the notes, and find this. Or sum of the books, they can write that R2 is equal to, let's say, R1, then you have 1 plus what is theta, and then say about theta 2 minus theta 1 times alpha, this way. So there are different styles of writing the same equation of temperature, of variations of resistance with the temperature. Okay, so it should not be confused. Or R2 can be R at any temperature theta. This is R naught, 1 plus alpha, open bracket, theta 2 minus theta 1, just like this. Okay?
Yes.
And you have to know definition of the terms. Have you finished your copy here? Or should I give you 1 minute? You finished. You? Now, why? So you want to copy from somebody. Why should you not copy from the blackboard? Where? Don't give up, elder. This is still introductions of current electricity. We didn't get yet in current electricity. It's still introduction. Then you have started to panic, to worry out. Don't worry out. We are just going slowly. And that's how advanced physics it is. Okay, so let me deduce some of the formulas which actually we'll be using from this general formula. So let me recommend that in this topic we'll be using this formula. So the temperature, resistance of the conductor at any temperature, and here we have 1 times alpha times small change in order in resistance. So let me recommend this general formula. So listen. Again, later on we can be dealing with this case, but let's say that we have maybe 2 cases. Listen. So the first case you have R1 is equal to R naught, then 1, then alpha, and change in temperature. Okay? And we have one conductor which has been, which you want to determine its resistance in different so let's say this is change in temperature 1 in different conditions. So different temperature change. Listen. So this might be question 9. Listen. Then we have the same conductor, one determines its resistance at another temperature, where we still have, or we heated it from the initial temperature. We have 1 alpha, small change in theta 2, like this. This is equation 10, for instance. So we'll be given the information for equation 9, but we'll also be given maybe the information for equation 10, except maybe another 2. It's not known, right? So how can you determine? So we can take equation 10, let's say, over equation 9. So we have what? R2 over R1 is equal to what? Is equal to R0 1 plus temperature coefficient. Remember that this is the same material, so temperature coefficient of resistance will be the same. Divided by what? R naught. We have 1 plus alpha, change in temperature 1. So R naught and R naught can cancel. So you can find that R2 when R1 is given, then you have 1 change in theta 2 over 1 plus alpha change in theta 1. So this is another formula that we may use. Let me deduce a final formula, then we'll be doing examples. The students say, sir, today there's no examples for temperature coefficient of resistance. You're just deriving formulas. And because you have learned and covered them, so you enjoy while your students here are getting pains in your mind. This is tough or difficult and whatever. So from this equation, R theta is equal to R naught, 1 plus temperature coefficient times change in temperature like this. We can make this the subject. Sometimes some of the questions will give you R theta, R naught, and change in temperature. You have to find what the temperature coefficient of 40 of resistance. So to make this item the subject, we have divided by R naught, we have divided by resistance of the conductor before the rising temperature. R naught, this is equal to 1 plus temperature coefficient of resistance times change in theta. So then half R at the temperature of R naught minus 1 is equal to 1 minus 1 plus alpha change in theta. So we have resistance at any temperature of R naught minus 1 is equal to alpha times change in temperature theta. So you can divide by temperature theta, change in temperature theta, and divide on both sides by change in temperature theta. So this one will cancel. So temperature coefficient of resistance is equal to resistance at temperature theta minus R naught over R naught to change in temperature. So this is formula which will give you temperature coefficient of conductor. So now it's time for examples. There are some other students that are saying, let us see examples. So we ended in example 11 in session 7. So example 12 states as this. Temperature coefficient of iron. Temperature coefficient of iron is 6.5 exponent -3 Kelvin. If an iron wire has resistance of 2.6 ohm at 0 degrees centigrade. What will be resistance of iron at 100 degrees centigrade. So temperature coefficient of iron is 6.5 exponent -3 per Kelvin. If an iron wire has a resistance of 2.6 ohm at 0 degrees centigrade, what will be the resistance of iron at 100 degrees centigrade? So it's simple. Solution. First is 3. That are given. Temperature coefficient of resistance alpha 6.5 exponent -3 resistance is equal to 2.6 ohm. Then the initial temperature is equal to 0 degrees centigrade. Then I've been asked resistance at 100, which is R theta, or R at 100. This is what's required. Then the final temperature, which is the final, is equal to 100 degrees. Second step, call the formula that relates theta or not, and the change in temperature. So theta is equal to or not. Okay, so our theta is equal to our not is open bracket 1 plus alpha, then we have what? Final temperature minus initial temperature. So then the next step is just the computation. You are looking resistance at 100 for the resistance at 0 degree, or at the initial temperature it is 2.30, 2.60 ohm. 1 plus what the temperature coefficient of iron? 6.5
exponent -3 per Kelvin.
-3 per Kelvin. Then what the temperature? So the unit of temperature coefficient, you see it is per Kelvin.
Yes.
Or so you should not worry that the unit is per Kelvin. Temperature should be in centigrade as usual. Don't convey the temperature into Kelvin because the unit of temperature coefficient of resistance is in Kelvin. So whether the unit is in Kelvin or in centigrade, there's no conversions of temperature to express the temperature or to convey temperature from centigrade to Kelvin. We don't need it here. Are we together? Yeah. So be careful about that, because I know some students can say, because temperature is in, because the unit of temperature coefficient of resistance is in Kelvin. So what the final temperature? It's 100 minus 0, like this. So just the matter of computation. Simply you have resistance, you are looking at resistance at 100, you have 2.6 ohm, and here we have 1, and then here we have what? So it's saying plus 6.5, so this 6.5 exponent negative 3 times 100 like this. So use your scientific calculator and find resistance at 100. So resistance at 100 is 4.29 ohm. 4.29 ohm. So you see that the fractional, compare 4.29 and 2.6. The fractional increase due to the increase in temperature from 0 degrees centigrade to 100. So therefore, resistance of iron wire is 4.29 ohm. Simple like that. Example 13. If resistance of the wire is 1.7 ohm at 20 degrees centigrade, find the resistance at 0 degrees centigrade and 100. 100 degrees centigrade for copper. Given that the temperature coefficient of copper is 0.00393 per degree centigrade. So the unit of temperature coefficient can be per centigrade or per Kelvin. Okay, so if resistance of the wire is 1.72 ohm at 20 degrees centigrade, find the resistance at 0 degrees centigrade and 100 degrees centigrade for copper, given that the temperature coefficient of copper is 0.00393 centigrade. Solution. The first step, we say that's data given. So if resistance of the wire is 1.72, resistance of the wire at 20 degrees centigrade 20 degrees centigrade is 1.72 ohm. Initial temperature is equal to 20 degrees centigrade. Find the resistance at T. So resistance at 0, which is R0, is required. And resistance of the conductor at 100, which is R100. This also is required. Temperature coefficient of copper is 0.0393. Second step. So you have to recall the formula. So the formula, resistance at any temperature theta is equal to R naught, means resistance at 0 degrees centigrade, 1 plus alpha times change in temperature. So now the first step you have to find is, so to make R naught or R at 0 degrees centigrade, we divide by this, 1 plus alpha, small change in temperature. So resistance at 0 degrees centigrade is equal to resistance at temperature theta over 1 plus temperature coefficient, product of temperature coefficient, and change in what? In temperature. So R naught is equal to what? R theta. So R theta, we can say for this case, is R at 20 over 1 plus what? Temperature coefficient of resistance times change in temperature. So this is equal to what? R at 20, it is what? R at 20 is 1.72 ohm divided by 1 plus 0.00393, and change in temperature from 0 to 20 is 20. So you can find resistance. So therefore, resistance of copper at 0 degrees centigrade is what? Which should be less than 1.72.
1.58.
Or 1.595. 1.595 ohm. So again, you have to find resistance at 100. So resistance at 100, we may use two options. We know the R naught, or original resistance there, or resistance at 0. So we say that the third step, let us compute resistance of the wire at 100 degrees centigrade. resistance of Y at 100 degrees centigrade, this will be equal to R naught, which we have computed, 1 plus alpha, change in temperature. So resistance of the wire when temperature increases from 0 to 100 is equal to 1.595 1 plus 0.00393. 100 minus 0 is 100. So you just have to use your scientific calculator to do multiplication and addition in that stage. So the answer is 2.22. 2.22. So therefore, resistance of what? Of the wire, of copper wire, is 2.2 ohm. So regarding on this concept now, the exam 14 will be your homework. Which is still simple. The winding of meter has a resistance of 80 ohm at 15 degrees centigrade. Find the resistance of the conductor at 50 degrees centigrade. The winding of the meter has a resistance of 80 ohm at 15 degrees centigrade. Find the resistance of the conductor at 50 degrees centigrade if temperature coefficient, if the temperature coefficient of the winding is 0.04. Okay, so let me teach you how you can solve the following conceptual question, and then I will give to you another homework, which it will be also a little bit trick question. And before I give you that trick questions, let me teach you this conceptual question. And then it will be the end of session 8. So, page number 15. Concept. And I'll be guiding you to solve you might find that, or you might see that it's not a concept. But later on, when you'll be revising yourself, or you meet it in an exam, then you'll notice that it's constant. So two coils in series, have resistance of 600 ohm and 300 ohm. Respectively. The temperature coefficient of two coils is 0.1% and 0.24% respectively at 20 degrees centigrade. Those are the information that you've been given. So you as physicists define now Roman 1, resistance of the combinations at 50. Right now resistance of the combination. And now resistance of the combination at 50 degrees centigrade. So, what's the effective temperature coefficient of conductor? What is effective what's the effective temperature coefficient of, so what's the effective temperature coefficient of conductor at 50 degrees centigrade? So that's the question we have. Two coils in series have resistance of 600 ohm and 300 ohm respectively. The temperature coefficients of the two coils is 0.1% and 0.4% respectively at 20 degrees centigrade. Find the resistance of the combinations at 50 degrees centigrade. And what's the effective temperature coefficients of the conductor at 50 degrees centigrade? Okay, so you should be careful. You can pause the video and try to solve that question on your rough paper. And then once you finish, you can click the buttons of play. You can check the correct solution and compare with yours to know how far you are or what is your level of comprehending questions about temperature coefficient of resistance of a conductor. We have two coils in series have resistance of 600 ohm and voltage and 300 ohm respectively. We'll be given the temperature coefficient at 20 degrees centigrade, and we have to find resistance of the combinations at 50 degrees centigrade, and what's the effective temperature coefficient of conductor at 50 degrees centigrade. So the first step that are given okay, so you have two coils in series. This means that you have one coil and then you have another coil. So this is your conductor. So let's say that here we have resistance 1 and this is resistance 2. But this conductor has been placed in 20 degrees centigrade. So we have its linear, its temperature coefficient, and also here we have its temperature coefficient too. Okay, and then we're being asked to find what R at 50, and this one is R at 50, and we have to find what the resistance of combination. Okay, so from the data given, we'll be given what the initial resistance at 20. Resistance of the first coil, equal to, let's say, 1 at 20 is equal to 600. Then the resistance of the second coil 2 at the same temperature 300 ohm. Temperature coefficient of first coil alpha 1 will be given 0.1%. So you have to convert this 0.1%. What does it mean? 0.1% means 0.1 over 100. This will make 0.001. Is it? No. We make 0.001. Then you have temperature coefficient of second coil. This is equal to 0.4%, which means that what? 0.4 over 100. This means that is 0.004. So what's required? The required is resistance of combinations of two coils. That's what is required. So the second step, when you recall resistance of the conductor at any temperature, which is equal to R naught, 1 plus temperature coefficient of the change in temperature. So we can say that R theta which is R at 50 of first coil. This is equal to what? R1, 1 plus alpha 1, change in temperature, because the temperature for the two conductors will be from 20 to 50, right?
Yes.
So change in temperature will be what? 50 minus 20, which is equal to 30. Then R at 50 of second coil. This is equal to R2, 1 plus alpha 2, change in theta. So combination, resistance of combination, resistance of combination is equal to what? Is equal to R at 50 of first coil plus R of 50 of second coil. So this means that what? R1, 1 plus alpha, change in temperature, plus R2, 1 plus alpha 2, change in temperature. So steady state, change in temperature for this case is equal to final temperature minus initial temperature, which is 50 minus 20, which is equal to 30. So resistance at 50 of combination is equal to what? R1, which is 600, 1 plus, then alpha 1, which is 0.001, times change in temperature, which is 30, plus R2, which is 300, 1 plus 0.04 times 30. Okay? This is the resistance at 50 of the first coil, resistance at 50 of the second coil. Okay?
Yes.
So the answer for Roman 1, resistance of combination, so just use your scientific calculator, resistance of combination at 50 degrees centigrade is, so if you complete the first one, you'll get 618 degrees ohm. The other one will be 336 ohm. So if you add them, we have 14. 8 plus 6 is 14, we keep 1. We have 4, then 1 is 5. We have 9. So resistance of combinations is what? 954 ohm. So the next question, what is the effective temperature coefficient of conductor at 50 degrees centigrade? Would you think that the temperature coefficient will change? You can do Roman 2 with 2. Remember that Roman 2 is this one. But There are two methods that you can solve from and to what's the effective temperature coefficient of a conductor at 50 degrees centigrade. But let me teach you the simplest one. The simplest one is this. Whether the temperature of the conductor will change, the temperature coefficient of resistance will never change. So because the temperature of these combinations has changed from 20 degrees centigrade to 50 degrees centigrade, it does not affect the temperature coefficient of the conductor. So to get effective temperature coefficient of the conductor in the simplest form, this is Roman 2. So effective temperature coefficient is equal to temperature coefficient of the first conductor plus temperature coefficient of second conductor. Okay? So if that's the case, we know this one was 0.001 plus 0.01 bar per centigrade. So therefore we say that effective temperature coefficient at 50 degrees centigrade is 0.005 centigrade or 0.1%. Okay, so it's a time now. Let me leave you the last homework and we call the end of session 8. In this example, 16, 17. Huh? 16. So it's concept. It's homework 8. So you have 2 questions for homework 8. This question you can refer a book called NELCON or Physics in Advanced Physics by NELCON. So refer Advanced Physics. Right now, I don't remember which edition, but I think 7th edition. Yes, 7 editions. Page 308. In an experiment carried as
Good question. Effective temperature resistance. When you had addition, you had 0.01 to 0.5.
so it's 0.5.
In addition,
This is 0.4. Thank you, Mr. Francis. So in an experiment carried at 0 degrees centigrade, A was 1.2 meter nickel wire of resistivity of meter and diameter of 1.2 millimeter, and that can be is silver wire of 0.8 millimeter diameter. And the resistivity is 2.8 with -8 ohm meter the ratio of resistance A to B was 1. It's 2. What was the length of B? What was the length of B if the temperature coefficient of nickel A is 0.004 centigrade. And the temperature coefficient Tanzania silver wire is 0.003 centigrade. Second question. What will be the ratio of the resistance if temperature was increased to 100 degrees centigrade, so what will be the ratio of resistance if temperature was increased to 100 degrees centigrade? So let me read the question again, because some students used to say, oh, sir, I was not reading clearly the syntax of your handwriting is not clear to me. In an experiment carried at 0 degrees centigrade, A was 1.2 meter nichrome wire of resistivity 100 to negative 8 ohm meter and diameter of 1.2 millimeter. And B is silver wire of 0.8 millimeter diameter and resistivity of 42.8 to negative 8 ohm meter. The ratio of resistance of A to B was 1.2, Roman 1. What was length of B if the temperature coefficients of nichrome A is 0.0004 per centigrade, and the temperature coefficients of the germanium silver wire is 0.0003 degrees centigrade. Second question. What will be the ratio of resistance if temperature was increased to 100 degrees centigrade? So try your level best to think, to apply all the concepts that I've taught you from the beginning of session 8 to the end. Remember also relationship between resistance and resistivity, and you have to be a little bit creative or innovative in dealing with the general formula of general formula of determining the resistance of conductor at any temperature. So ladies and gentlemen, this is the end of session 8. I would like to invite you in session 9 when we'll be continuing on learning about conductions of electricity in metals, because still this is one of the concepts. We have covered this. Maybe we can deal with it in some few cases later on, but we are done. So it's a matter of yourself to do more practice on solving different questions. And I have just two announcements before I end up this session 8. The first announcement, we have also created or established the Tanzania Online Advanced Library, where we equip our students with materials such as notes and even also books. So right now, I would like just to show you some of the books that we have. The first book is this one, that is called the Physics Syllabus for Advanced Secondary Education from 5 to Form 6. It has been written by Tanzania Institute of Education, so you can order this or a copy of it. The second ones, we have Principle of Physics. You can have Principle of Physics 1 or Principle of Physics 2. This is the sample for the Principle of Physics 1. You can order it. Then these are the questions and answer books. Advanced Physics 1 review, Advanced Physics 2 review. You may order them. We are just servicing our students. And the way that you can place your order, or you can order, is just to send an SMS to this telephone number 0759745331, and then we'll be calling you back in order to give you some instructions how you can order these books in any regions of Tanzania, except for the international students you cannot access at this moment. So next time, again, that in next sessions I will let you know that maybe the price of these books and price of the sum of the items that we have them in our library. Secondly, and the last announcement, also you can offer your free Thanksgiving in order to support the running cost for this program, because we have a great visions of recording more videos and it's expensive. And that's why we are inviting you to join us in order to make sure that we achieve the main objective of the ASO of recording at least more than 600 videos of advanced physics, advanced chemistry, advanced mathematics, and basic applied mathematics. So, because we have had an opening prayer, so let us pray to give God thanks for what He has done to us in this moment of learning current electricity. Our Father who is in heaven, we come before your presence. We say thank you for this opportunity. Say thank you for what you have taught us about temperature coefficient of resistance. Father, I dedicate your physical, your local, your national, your international students in your hands for you to teach them more about temperature coefficient of resistance of the conductor. And let them understand and keep this information in their minds and use it for the rest of their life, Father. Father, I thank you for the opportunity you have given me, and I would like to just handle this lecture or this session 8 in your hands so you can distribute it to every student across the entire country of Tanzania who is in need of these contents, or any international students, for the present and future generation. We give you all the glory and the honor for everything that you have done, for everything that you are doing, for everything that you are going to do into us all. In Jesus' name, amen. So may God bless you and keep you until we meet in session 9. Keep enjoying the beauty of advanced physics. I love you so much. See you in the next session.
Mungu ibariki Tanzania.